So, and the later part is here. Okay. Yeah, welcome to this talk. I have the pleasure of reporting to you what we've done in the Helmholtz-Zentrum Berlin regarding perovskite solar cells. By the end of this talk, you will know mostly three things. So first of all, why it's worthwhile to adopt SAMs into your workflow if you haven't already. And I mean, why it could pay off to invest further time in the development of self-assembled monolayers as charge selective layers. And what I also want to do is to fuel the discussion about charge extraction in the community. So we talk a lot about charge losses, right? Recombination losses, mainly because I think it's easier to measure than charge extraction, since it's a transient process. I also want to give you the, or to emphasize the importance about energy level alignment. Then again, why we can't measure it really. I mean, sure, there's some discussion, and the measurements of the energy level alignments. And what we can learn from these small molecules right here that give us an experimental variation in the realms which we want to investigate, usually with alignment measurements or charge extraction measurements. So this is a device-oriented talk, and the device I was mostly working on in my PhD is depicted here. Like, pretty simple. We have two electrodes, copper and ITO, the perovskite in between, and when you zoom in just close enough, then you would see organic molecules in this interface that self-assemble, and most of my work was dedicated to optimizing the formation of these molecules, then asking the question, what is the whole accepting layer level doing, and which energy levels do these molecules have? How fast do holes get extracted? What can they tell us regarding photoluminescence correlations to the device performance? How they can be incorporated in tandem solar cells, here depicted as a rough CIGSe bottom cell. That is no problem for the SAMs to cover. And the NREL efficiency chart was also playing a role, as you will see. But first, let's take a look at the basics. So we start with a simple solar cell. we like these PIN solar cells in our group because they're low temperature processable, and in principle they're rather simple. They're close to the theoretical simplicity of a heterorod junction solar cell. So we have a perovskite sandwich in between, and ideally you want to choose a perovskite composition that is quite reproducible and robust to make. And then when you just take care of contaminations in your powders, it's usually no problem. So then you can do the investigations of the interfaces that are extremely delicate, as people have found out in literature as well. So usually the perovskite is not the problem, but then the interface is to the charge selective layers. In PIN solar cells, the N-type layer is mostly constant, so it's fullerenes. I've also explored a lot of alternatives, but there's nothing like C60 or PCBM. They just win in most cases. But for the P layer, there's a lot of play. So organic chemists like to synthesize a lot of molecules, and there's a lot of possible molecules that are intrinsically hole selective, or just by their energetic nature are hole selective. First, now, and this is why we looked at the P selective layer and wanted to discuss the implications of variations thereof. But as I said, back to basics, what does a solar cell do? So the sun shines and we create a current, which in other words is electrons flowing in one direction, and because it's a circuit, electrons get also fed again into the semiconductor. Or to simplify it for some physics perspective, we say holes get extracted as well. And what is important to keep in mind is that this process, it can be steady state process, but it's by nature we need a non-equilibrium state to generate a current, right? And the only driving force getting the charge carriers out of their thermal equilibrium is coming from the photons by the absorption. And then during their excited state, we have the opportunity to extract them. And a rival process is non-radiative recombination by traps, by interface recombination, and so on. Let's look at this in the energetic picture, and we see this that you see also in textbooks and a lot of discussions in literature. So the energy level alignment, or the energetical schematical view. Starting with the perovskite, when we draw the band edges, this has proven useful to discuss implications, or to predict how a solar cell could work. So solar cell here, the absorber, depicted by the conduction band minimum and the valence band maximum, holes and electrons, as in the picture before. And the task is to get the electrons to the electrode and the holes to the other electrode. And we help them by including some ladders, right? So some energy levels that they can hop onto and go into the electrode. Ideally, they only let through one charge carrier and not the other. The main question is, what we investigate is, what are the losses happening here in this process? And what I've done is looked at this experimentally. So we have a lot of different hole-selective layers that are self-assembled monolayers for a good reason, because ideally when you want to study such a system, you want the perovskite to remain constant, the perovskite quality, the crystal quality to just don't change, because usually you put the perovskite onto the hole-selective layer, and thus you could change decrystallization, which would make evaluation quite difficult, right? Then you only want to vary the energetics here while keeping the chemistry constant, so the interaction between the hole-selective layer and the perovskite. And you don't want any parasitic resistance to mess with your fill factors and so on, which makes things, again, much complicated. And here's where self-assembled monolayers come into play, because usually the chemistry remains the same, and just by slight changes in the atomics, you get wildly different energetics. There are a few things that can go wrong at the hole-selective interface. So this is the ideal case. Everything is aligned. You get the holes out of their system, out of the absorber. But you can have traps in between, which are attractive to both electrons and holes. The worst traps are those in the middle, because then the rates are the same and you lose a lot of charge carriers. You can also have a barrier in which the holes would need additional energy to enter the hole-selective layer to then go to the electrode. Then you can also have a not aligned interface. So you would just lose energy here, free energy, or poor selectivity, where both charge carriers go in and recombine there. Ideally, you have charge selective layers that act as semi-permeable membranes. This term was coined also by Shockley earlier, but also by Würfel. So only let through one. And this can be done by multiple ways, right? So energetics is one thing, just putting them barriers. Or you can also do it by conductivity asymmetry. So this is why doping is for, and or some intrinsic molecular asymmetries. And usually, hole-selective layers are processed by spin coating or sputtering, and what's often used is PTAA, which is rather expensive. And these processes all have their variations, which then introduce variation in the complete solar cell. And the nice thing about self-assembled monolayers is that everything happens by itself, right? So the beauty of it is you encode the function of the complete layer in the design of the molecule. And here, especially by phosphonic acids, that when they see OH groups on the surface, they react to form water in different modes of binding. And you get the same layer really reproducibly, and you can be sure there's usually, if everything is done right, usually one layer. And the advantages are obvious. You don't need more material. I mean, it's the minimum material you can use. It's conformal, doesn't matter how the surface looks like. Scalable, and you can build a model system upon that. So without any weird other variations coming from the processing parameters. So then we started off, and honestly, I have to admit, we just used the molecules that were basically in a shelf somewhere, and the idea was born. And Artyom, that was visiting me during that time at AZB, we did this together. So we had this molecule here first. Oh, this one was the very first. So there's a hole-selective fragment that is known among organic chemists, I guess, and an anchoring molecule, an anchoring part. And the first tests, after figuring out how to process them, were not very convincing, but still surprising. So it's with a monolayer, we could reach some JV curves that you can see here. So PTAA at that time, 18% was fine, and 17% for the best V1036 cell. And then there was a big difference to this molecule right here, V1035, but it's only basically the variation, 2 anchoring groups. We thought this should be better. But all of them are better than nothing. So there's some hole-selective property going on. And then the idea was, well, the VOC is rather low. It was 1 volt only compared to 113 or 111 for PTA. And we thought it has to be the ordering, right? So probably it's a very chaotic layer. And let's increase the ordering. There was literature on that by putting in some spaces or fillers. So thereby you can promote interaction between the molecules so they can self-order themselves. And by introducing these fillers, so also basically a self-assembled monolayer, but without a function, we changed also the contact angle. And by reaching a contact angle that was similar to PTA, we got higher VOC. And the highest VOC was then 1.1, almost reaching levels of PTA, but not quite yet. Now then, to our surprise, it was not the ordering that was increasing the VOC. It was the only correlation we found was the ionization potential. So the highest VOC devices were those with the highest ionization potential of the ITO SAM substrate. Then we went on and tried more molecules. So the first hint was, okay, it has maybe it's the ionization potential. Let's go for higher values even. So PTA was at 5.2 electron volts. Maybe 5.3 or 5 would be better. And then after some tries, it indeed was the case. So we had some different molecules to try out. And then 2 molecules stood out that were beating PTA and the VOC. Neo-2-Pax and 2-Pax. And 2-Pax in this case was an ionization potential of 5.6. So rather high. Neo-2-Pax very similar to PTA, but still a higher VOC, which is interesting. So it's already these 3, PTA, Neo-2-Pax, 2-Pax, is kind of a model system. Same ionization potential, but higher VOC, higher ionization potential, and higher VOC. And indeed, the solar cells performed quite well during that time, 2019. It was state of the art for PIN cells in that bandgap range. And V1036, well, never made it above 18%, but I mean, you wouldn't believe it, but now V1036 is proven useful for other perovskites, for namely for inorganic perovskites that have a different energetics as well. But yeah, this was quite an achievement for us. And what stood out is that everything correlated nicely. So every measurement you did, I mean, be it energetics or photoluminescence, as summarized here, it correlated to device performance. So here, hole-selective layer, and then the stars are the reached VOC values. The bars are TRPL decay times, and the blue spheres are quasi-Fermi level splittings. So basically a measure of the photoluminescence quantum yield. And both, everything correlates. And a big surprise to me that I struggled to understand for a long time is why with 2-Pax, you even get a higher TRPL lifetime than when you just put perovskite on quartz. And usually quartz is considered perfectly passivated. So that's why I concluded at that time, well, 2-Pax, this very simple molecule basically creates a perfectly passivated surface on the ITO. And the ITO has a lot of electronic traps for electrons especially. So just by this very simple design, it's possible to make ITO basically lossless. And yeah, I mean, one take-home message already is the simpler the molecule, the better the cells. And it went on and on. Of course, I further optimized solar cells. And with 2-Pax is even able to sustain over 1.28 volts VOC at a 1.68 EV perovskite at a high fill factor. So a tiny molecule that is able to really outperform everything else that we've seen. And now to the ultraviolet photoelectron spectroscopy measurements. I told you already it also correlates, and we extended this to even more SAMs, and it still correlates. And if you go above, then you get F shapes as expected. But yeah, here's a very simple picture. The reality is always more complicated, but a simple picture of the energetic schematics. So again, perovskite, the work function is to the red line. and then valence band maximum by the valence band onset in the UPS. And when you align to the vacuum level, then you see, well, it's aligned to 2-packs and not so aligned to MEO 2-packs, or MEO 2-packs PTA are very similar. So there seems to be a chemical difference in the traps, since MEO 2-packs giving higher VOC, and V1036 is not aligned at all. So basically, this is the case that I've shown in the beginning. Not, I mean, poor selectivity, right? So you probably electrons get into the system here as well. But here, a big disclaimer: values that you see in like these here, usually they are very inaccurate just by nature, right? By the evaluation method. And we never know what happens under operation. So usually we just take a sample and measure only the hole-selective layer on top. But then in the solar cell, I mean, you put perovskite on top, there's electric fields going on, and you never know what happens during operation. For a deeper look here, it goes quite far. I recommend looking at the paper by my colleague Doro, where we revisited the determination of the valence band maximum by a technique that is highly sensitive, which is constant Finland yield photoelectron spectroscopy, photoemission spectroscopy. And there basically we find out that you need 5 or 6 orders of magnitude and then some modeling to really be able to determine the valence band onset. Okay, but now with this disclaimer, let's go back to the simple picture. And let's just say that, but trends are still in line. So just experimentally, the trends in these simple pictures are still in line. And then in the simple picture, the main difference is that between 2-packs and V1036, is that 2-packs has probably a higher selectivity, right? The holes can get through without any energetic lift, energetic loss, and then recombine with the electrons in ITO, or to say better, ITO can resupply the electrons. In V1036, the energy level is not, it's somewhere in the middle of the band gap of the perovskite, if the values were accurate. So we get the high VOCs, but what's with the fill factor, right? So now the process is what speed or how quickly can the holes go into the HOMO level of the 2-packs and then further on to the ITO work function level. Well, this is a question not answered so often in literature, but it should be, because it's rather important. So when you look at the fill factor values of perovskites, it's rather embarrassing looking at the literature, especially compared to other technologies. So here we see record fill factor values that were reached with other technologies. Gallium indium phosphide, so 3,5 is gallium indium phosphide N3,5 that usually reach very high fill factors, have low ideality factors, they're close to the detailed balance limit. Silicon, because of its indirect band gap nature, also reaches high fill factors. But perovskites, I mean, usually you're quite content with 80 or 81%, but 85% should be, but also 90% should be reachable with perovskite, with the perovskite VOC. And this, although the areas of the solar cells are rather small, so around 0.1 square centimeters in literature, and still 81% is considered a good fill factor. This is surprising because usually the VOCs, they easily reach over 90% of the radiative limit. And the main cause seems to be that there are high ideality factors in perovskite solar cells. And what you rarely see, but in the last year, you've seen this more often, but what you rarely see is the high VOC combined with a high fill factor, especially in PIN solar cells. So the task is to further understand the charge extraction. How can we do that? Well, charge extraction in itself is a transient process. So let's use a transient method. And the transient method that I was familiar with was transient photoluminescence. So here, let's do a very simple experiment. Let's take a sample that on one side can extract charges, on the other cannot extract charges. So ITO spot that wanders off into only glass, right? And then there's a SAM on top that binds to both glass and ITO. now you take your spot, and when you go through that, you see these TRPL curves. So a fast decay when there is ITO below, and slow decay in the beginning when there's no ITO below. And you get every value in between when you just go through this layoff. So this tells you already, I mean, the beginning here has to do something with charge extraction, right? So holes can go into the ITO recombine there. So let's exploit this, right? Let's use different monolayers. We measured the perovskite quality remains the same, crystalline, and well, you change the energetics a bit, but you don't change the chemistry. So what you get then are these transient or TRPL transients. And a good thing to look, I mean, usually in literature you see you can extract a lifetime somewhere just by mono exponential fit. But what's really useful is to transfer the whole curve into a lifetime plot, basically by the differential lifetime with this formula, right? So you take 1 over the derivative of the logarithm. And what you see then is the steep rise. And differences in these rises or in these rise times can give you differences in charge extraction, because, I mean, we were lucky at that time. The Kirchhoff's group or Benedikt Krogmeier published a simulation just on this situation, but on the electron side. And they get pretty similar curves, right? So here for low injection, you see this curve here, and they simulated, well, this is indeed a transfer. And then it stays constant, ideally. So here, this is then dominated by bulk recombination. The good thing here is the well-performing SAMs, they have a high bulk lifetime, or they enable high decay times in the bulk. So it makes differentiation easy between the beginning of the transfer to end of the transfer. If you take PTA, for example, it's not, you won't see with triple cation perovskite, it's just mushy. You don't see this nice curve that'll just look like in the simulation. So again, this is a hint. SAMs enable a model system. You can, because of the well, transfer seems to be fast, fill factors are high, and the bulk lifetimes remain high. We can exploit this further and do this for different intensities now to get more quantitative, right? And what you know in charge carrier recombination, it scales with the charge carrier density, and the different recombination channels scale with different exponents. Here for the case now 2-pax versus Me 4-pax. So the winner in this case, so the fastest molecule that we have is Me 4-pax. Methyl group on the 4-pax core, basically, that's depicted here. And you have this mono exponential decay as it should be. And this stays until 10 suns. And then you see a small deviation here beginning 33 at 100 suns. You see the deviation from mono exponential decay. For 2-pax, this effect is stronger, right? The deviation already happens at 3 suns. And I mean, at 100 suns, it's pretty obvious. And you can use this deviation, so basically this area below the transient, for calculating the ratio of bimolecular recombination to monomolecular recombination. And by comparing this, you have a quantitative difference in charge extraction efficiency. And by this, we knew Me 4-pax can extract with 10 times higher flux than 2-pax. And at the same time, I mean, we make sure that the excitation conditions are the same. So as I said, it scales with different exponents. And when you just took the peak of the TRPL transient and plotted here, so this is the mono exponential part and the bimolecular part, and one sun is somewhere here, and you see all of them, they follow the same trend. So we did a fair comparison, is what I want to say. Now, okay, it was exciting. We used TRPL for finally quantifying charge extraction in perovskite solar cells. Can we confirm that now with another technique? And this was quite useful as well. I mean, we can measure for that surface photovoltage. So instead of measuring photons, we just measure the voltage, which is the main thing that a solar cell should do, right? So you start with perovskite, and usually when you extract charges, you have an asymmetry in charge carrier concentrations between electrons and holes. And this should be visible in the sign of the photovoltage. So upon excitation, you get some redistribution. And in this case, then you measure by transient means a positive photovoltage, which means holes get to the surface first. This is so the perovskite is not perfectly intrinsic. And then decay off, and there's some capacitive effects probably also happening. Now, when you extract holes with SAM, so putting an HDL here, you extract all the holes into the ITO. Well, I mean, ideally all the holes, and so the surface photovoltage then is negative. And then you just let the system relax, and you again land at 0. Now again, let's use the power of SAMs to build a model system. So how can we now test whether this rise here, which pretty much is in line with the TRPL decay, the first steep one, how can we confirm that this is connected to charge extraction? We can do this by changing the isolating part of the SAM. So this one, this aliphatic chain is basically isolating. So doing a series here of 2, 4, and 6, you see this also reflected in the series resistance then in the JV curves. And nicely enough, now again measuring with these different molecules, this transient surface photovoltage, you see here the rise times are different, right? It's slower for the larger aliphatic chain. So we can say the slope here is indicative of the charge extraction. And now it's compared again 2 packs with my 4 packs, and we see a confirmation here, which we also published in a year ago. This is good because TRPL just stops functioning as soon as there are no photons anymore, right? Hitting the sensor. But transient surface photovoltage goes until 1 second. I mean, it's a huge time domain. You're not dependent on the photons to tell you the story. And but what about this slope here? So we know this slope, and what about this slope? And this slope can be done, can be measured basically by cross comparison to PL. So when you have the same box, the same measurement, measure PL and SPV, you see that the second slope has to be by molecular recombination. So both experiments are complementary. If you have both, you basically know most of the charge extraction and concurrent recombination. This was a simple system, right? With me 4 packs or 2 packs. Using a more complex SAM, you get transients like these, but we were able to find out what these by rate equations, basically what these processes are corresponding to. There can be electron trapping, extraction, bimolecular, or recombination, detrapping again, and then the back injection. The whole story in one transient. Now, we also, I mean, we just looked at the hole-selective side, but we only get a bump in fill factor if the electron selective side is not limiting, right? But for this, I mean, we also can use TRPL combined with even faster methods. And we basically see where they this experiment. So we excite with blue light on the C60 side versus the non-C60 side. And this decay here also has to be charge extraction, because it lifts off from the mono exponential part at longer times. And by this, we know that C60 is really fast in charge extraction. So it's, when you compare it to the whole extraction side, it's around 100 times faster. So there's still a lot to do in the whole selective side. So electron selective side, regarding the how quick electrons are being extracted, no need to worry about that. Now to the solar cells. So all these informations also translate in the fill factor of the solar cells in the JV curves. Again, the model system here, MEO 2 packs, 2 packs, MEO 4 packs. MEO 4 packs is, well, reaches the 84% mark. And just when you do a pseudo JV curve, you know, 86 should be possible without any transport losses. And the main reason here, the main difference between 2 packs and MEO 4 packs is the low ideality factor. So now we have achieved low ideality factor combined with a high VOC when you passivate the C60 interface. Good, so we have a simple PIN solar cell with high VOC, high fill factor, which can be put into tandems, right? And one of my favorite projects was putting it into CIGS perovskite tandems, because SAMs basically enable this, right? So we have a rough surface. When you use a classical hole-selective layer, usually they don't grow that nicely on a rough surface, but for the SAMs, it doesn't matter. You just dip it for a few minutes and you have a perfectly hole-selective, fully covered surface. And 2019, we certified a world record of 23.3, which later, by using May-4 was 24.2. And the currents in the tandem cell are comparable to silicon currents. So, and also VOCs can be high for CIGS. So there's nothing basically holding back. Mainly, it's the processing. As you see here, the shunt resistance is not so great. Mainly, this rough surface also makes it difficult to not have any dust particles at all. So it's usually processing that limits further CIGS tandem efficiency, I think. But the nice thing is, since it's a double all thin film solar cell technology, you can have flexible solar cells, which also reached over 20% in my works. Now going to silicon solar cells, there it's easier to get high fill factors because of the flat surfaces. And the use of May-4 has given us this marks in the annual efficiency chart. So here you see the JV curves in red with May-4 versus PTAA. The fill factor is basically what sets it off. Yeah, almost 40 milliamps in some current generation. And the stability was also nice. So 95% after 300 hours in air was still retained. And so what's to take home is the fill factor benefit from the single junctions also transferred into the tandems. So that's how we know. I mean, it's one of the limiting factors, right? Hole extraction efficiency. We also went further. The 29.8% that we reached in tandem solar cells we reached with a nanotexturing, done by Christiane Becker's group and Philipp Tockhorn. And here again, the advantage is that SAMs don't care about the surface, right? So when you zoom in, it's just still flat surface for them. So they used all kinds of different nanotextures and found, well, sinusoidal textures were quite nice for perovskite quality, and advantage in NGSE was observed. And then by electroluminescence, we also estimated the maximum efficiency the tandems could give. And by that time, I'm sorry, so basically we have pseudo JV curves of the different subcells. The idea is you inject electrical current, and the electroluminescence gives you something about the internal fields, right? But internal fields are not affected by the resistances. So that's how we can have the pseudo JV curves of the silicon and the top cell. And together we estimated, well, if we reduce transport losses further, it should be possible to gain over 31% efficiency. And again, the pseudo fill factor 88% should be in principle possible, but we are almost at 80%, which there's a lot of room still. But okay, we estimated over 31%, and as you know, CSEM, EPFL have reached 31.3% recently, which is quite nice because it raises the spirits as well and gave our group again some motivation to further optimize solar cells, and we did optimize, especially Eike and Sylvia. We recently certified as well 31.5% at the SD lab. And the nice thing here, it's still SAMs, and the VOC that we reach now is up to 2 volts. So it's the SAMs continue to surprise us that high photovoltages can be sustained by just these small molecules here. And what's funny, it's the MPP is at 1.7 volts, so you can drive basically water splitting, for example, or yes. But so I'm coming to my conclusion. What's very exciting for me is that SAMs are further spreading. So, for example, in co-evaporated perovskites, they seem to be rather stable. So we have also a publication with no loss after 1,000 hours of MPP tracking. It doesn't matter which nanotextures we use. There are some lead-tin perovskite solar cells using 2-packs, some organic solar cells using that, all perovskite solar cells. They're compatible to industrial bottom cells, to slot die coating, and so I guess there's a trend. And the take-home messages that I want you to take is that SAMs, they enable very highly efficient and simple solar cells. What's interesting for me is that they enable a model system. So you can, either train your models or systematically investigate energetic alignment, or let's say, or charge extraction, which was interesting for me. Although energetic alignment, there's always some discussions. There are nice reviews also, for example, by Philipp Schulz or Dorothee Menzel of our group that are to read upon. They enable faster research, and what's still to do is to further accelerate hole extraction. This is what I want to say, and also investigate stability at 85 degrees. Because it seems, at least the chemists say, this linking chain here could be a weak point, but it's easily fixable. And there are some papers already coming, but it's good if more groups work on that. With that, I want to thank you for your attention. Thank my group, of course, and PVComB for providing us the bottom cells, and my colleagues at QYV from which I learned a lot of stuff for photoluminescence and the measurements. Okay, thank you. I'm open for questions.